Hold a magnet in your hand and slowly bring it close to a piece of iron. The iron slides toward the magnet without ever being touched. There is no rope, no airflow, no visible mechanism connecting the two. Between them is what looks like empty space, and yet something happens. Motion appears where none seemed possible. This simple experiment already separates magnetism from most forces people encounter in everyday life. A push usually requires contact. A pull is typically transmitted through something tangible: muscle, rope, air, water. Magnetism is different. It works across emptiness, and that emptiness does not merely sit there doing nothing. The space itself participates. This feature is the first clue to what magnetism really involves. Magnetism is not a mysterious substance leaking out of objects. It is not a hidden string pulling iron toward a magnet. It is a manifestation of something deeper, something tied to motion at the most fundamental level. Every magnetic phenomenon, without exception, can be traced back to moving electric charge. Take a simple example: a current flowing through a wire. The moment electric charge begins to move, a magnetic effect appears around the wire. Compasses nearby deflect. Iron filings arrange themselves into patterns, turn the current off, and the magnetic effect vanishes instantly. The magnetism was not stored in the wire as a static property. It existed only while charges were in motion. Now consider permanent magnets, which seem at first to contradict this idea. They produce magnetic effects even when nothing appears to be moving. But when you look inside the material, motion is everywhere. Inside atoms, electrons carry electric charge and are never truly at rest. They occupy quantum states that involve circulation, angular momentum, and an intrinsic rotational property known as spin. These motions are not like tiny planets orbiting a nucleus in neat paths, but they still represent structured, persistent activity. Each moving charge contributes a tiny magnetic influence. In most materials, these microscopic magnetic contributions point in random directions. One electron's effect cancels another's. The net result is zero. That is why everyday objects like wood, plastic, or glass show no noticeable magnetic behavior. But in certain materials, iron, nickel, cobalt, large numbers of electrons can align their motions. When this happens, the tiny magnetic effects reinforce one another instead of canceling out. The material becomes magnetized. This alignment is not permanent by default. It depends on how electrons organize themselves inside the atomic lattice. A nearby magnet can influence this organization. When iron is brought close to a magnet, the magnetic structure of the surrounding space nudges electrons inside the iron into alignment. Small regions called domains grow and reorient. As more domains line up, the material responds as a whole and moves toward the magnet. The iron is not being pulled by an invisible hand. Its internal motion is reorganizing in response to conditions present in the space around it. That space is not empty in any meaningful sense. Around a magnet, space carries structure. At every point near the magnet, there is a direction and a strength associated with magnetic influence. Compasses detect it. Iron filings reveal it visually, tracing elegant curves that show how this structure extends outward. These patterns are not decorations. They reflect real constraints on how charged motion can occur in that region. The interaction is not just between objects. It includes the space between them as an active participant. This is a radical departure from the way forces are usually imagined. Magnetism does not act like a shove delivered at a distance. Nothing travels outward like a mechanical push. Instead, conditions are established throughout space that guide how charged particles behave wherever they happen to be. If a charge is present and in motion, it responds to those conditions. The force is not localized at the magnet alone, it is distributed. Motion appears again when we look deeper, because magnetism and electricity are not separate phenomena. They are two aspects of a single underlying interaction. Whether you describe something as electric or magnetic depends on motion, specifically relative motion between charges and observers. A stationary charge produces an electric effect. Set that charge in motion, and a magnetic effect appears. Change your frame of reference, and what looked magnetic can be reinterpreted as electric. The distinction is not absolute. This unity becomes clear in relativity. Electric and magnetic fields transform into one another when observers move relative to each other. What one observer describes as a purely electric force, another may describe as a combination of electric and magnetic effects. The physics does not change, only the description does. Motion weaves electricity and magnetism together into a single framework. Seen this way, magnetism is not an extra force layered on top of electricity. It is a consequence of electric charge combined with motion and the structure of space-time itself. The magnetic field is not a substance filling space, but a way of describing how space constrains and organizes the behavior of moving charges. It tells charged particles which paths are allowed, which motions are favored, and which are resisted. This perspective also explains why magnetism feels so strange compared to everyday experience. Most forces we encounter early in life are mediated by contact or pressure. Magnetism bypasses those intuitions because it does not rely on direct interaction between surfaces. It relies on patterns established throughout space, patterns that only become visible when matter capable of responding to them is present. The magnet in your hand does not reach out and grab the iron. Instead, it reshapes the environment around it. When iron enters that environment, its internal charges reorganize their motion to match the conditions already there. The resulting motion of the iron is not imposed from outside, it emerges from within. This is why magnetism feels almost magical when first encountered. Something happens across nothing, but that nothing is not empty. It carries structure, direction, and constraint. Magnetism reveals that space is not a passive backdrop. It plays an active role in how matter behaves. In the end, magnetism teaches a broader lesson about physics. Forces are not always about direct contact or mechanical transmission. Sometimes they are about relationships, motion, and the structure of space itself. What looks like action at a distance is often the unfolding of local rules applied everywhere. When charges move, space responds. When space is structured, motion follows. Magnetism lives in that interplay, where motion, charge, and space become inseparable parts of a single story. What people call magnetism reflects electricity combined with motion. The two always appear together as parts of a single framework. This connection explains why magnetism links naturally to generators, motors, radio signals, and light. It extends far beyond household magnets. It reveals how space, motion, and charge cooperate at a fundamental level. And that cooperation acting silently through space gives magnetism its distinctive character. Simple to demonstrate, difficult to ignore, and impossible to separate from how nature organizes motion itself. To move forward without confusion, magnetism needs a direct description, not just a list of effects. Magnetism is the part of electric interaction that appears when electric charge moves. Nothing extra gets added. No magnetic substance joins the story. No special ingredient hides inside matter. Motion alone changes how electric interaction works, and that change shows up as magnetism. This point often clashes with everyday expectations. Objects seem to exist first with motion added later. Magnetism flips that order. Motion actively reshapes interaction. Charges that move do not interact the same way as charges that stay still, even though the charges themselves remain identical. A straight wire makes this visible. Run an electric current through it and place a compass nearby. The needle turns. No charge leaves the wire. The wire holds no overall electric charge. Only one thing differs from the quiet wire. Charges inside move. That motion alters how space behaves around the wire. The space nearby gains direction, not a push away from the wire and not a pull toward it, but a circular influence surrounding the path of motion. That circular form often surprises people. Everyday forces tend to act along straight lines. Magnetism acts sideways to motion. Direction depends on how things move, not only on where they sit. This sideways action explains a key feature of magnetism. It redirects motion without changing speed. A charged particle entering a magnetic region curves instead of slowing down or speeding up. Energy stays the same while direction changes. This behavior drives circular paths in particle experiments and rotation inside electric motors. Nothing mysterious causes this. The rule linking force to motion places the magnetic influence at right angles to velocity. That single geometric fact explains a wide range of magnetic behavior without adding new assumptions. Permanent magnets fit into this same picture. No current flows through wires inside them, yet magnetism persists. The source lies inside atoms. Electrons carry charge and possess built-in motion tied to how they exist at very small scales. In some materials, large numbers of these microscopic motions line up. Their effects reinforce one another across large regions. That alignment produces a strong magnetic influence without any visible current. So magnetism never requires batteries or circuits. It requires moving charge, whether that motion travels through space or loops inside atomic structure. This leads to another point that often conflicts with everyday reasoning. Causes usually involve contact or direct transfer. Magnetism depends on relative motion instead. Two charges can interact magnetically in one situation and not in another. Even though nothing about the charges themselves changes, only motion changes. The observer's motion enters naturally as well. Electric and magnetic effects depend on how fast the observer moves compared to the charges. What appears as purely electric interaction in one situation appears as a mix of electric and magnetic interaction in another. Both descriptions follow the same laws and predict the same outcomes. This connection does not come from interpretation or viewpoint. It follows from how space and time relate to motion. Differences in measured distances and timing alter how electric forces distribute. Those alterations show up exactly as magnetic effects. Experiments confirm this relationship repeatedly. This leads to a strong conclusion. Magnetism does not add a new force to nature. It follows automatically from electric interaction combined with motion and the structure of space and time. Given charge and motion, magnetism appears without exception. That overturns another expectation. Magnetism often feels optional, as if certain materials simply possess it by chance. Physics treats it as unavoidable. Whenever charge waves, magnetism follows. Space plays a central role throughout. Magnetic influence occupies the region around sources rather than sitting inside objects alone. Every location carries direction and strength. Objects respond locally to the conditions where they are. Interaction spreads through space instead of jumping directly between objects. This description replaces the idea that objects reach across distance to influence one another. Conditions exist everywhere, and charges respond where they stand. Space takes part rather than acting as an empty stage. This view explains why many devices function. Electric motors rely on magnetic influence guiding moving charges through loops. Generators reverse the process, turning motion into electric current through the same interaction. Radio transmission and reception rely on changing electric and magnetic influences moving together through space. Light itself fits into this structure. When charge changes speed or direction, linked electric and magnetic influences travel outward together. Neither travels alone. Their mutual reinforcement allows waves to move through empty space. Vision, communication, and modern electronics depend on this behavior. Magnetism also explains why isolated magnetic charges never appear. Electric charge exists on its own. Magnetic influence always forms closed loops. Cutting a magnet never isolates a single pole. Each piece forms its own pair. Iron filings reveal looping structure because they align with direction at each point in space. At this scale and every other, the same rules apply. Inside atoms, inside machines, inside planets, and across stars, magnetism follows motion of charge. Size changes nothing about the governing principles. Taken together, magnetism stands revealed as the motion-dependent structure of electric interaction encoded into space and time. It redirects motion without altering energy. It forms loops rather than sources. It links electricity, motion, and light into a single framework. That framework explains magnets, compasses, motors, generators, radio signals, and light using the same small set of rules. And as those rules are followed more closely, magnetism appears less like a special trick of materials and more like an unavoidable outcome of charge refusing to stay still. That framework explains magnets, compasses, motors, generators, radio signals, and light using the same small set of rules. And as those rules are followed more closely, magnetism appears less like a special trick of materials and more like an unavoidable outcome of charge refusing to stay still. If motion of charge reshapes interaction so thoroughly, then interaction itself depends on how things move through space and time. That idea carries consequences that reach far beyond magnets. One immediate consequence shows up in how forces behave. Magnetism redirects motion without changing energy. A charged particle entering a magnetic region curves, loops, or spirals, yet its speed remains unchanged. Direction alters while energy stays fixed. That result feels strange at first, since many forces exchange energy directly. Magnetism works through geometry rather than exchange. It bends trajectories instead of speeding them up or slowing them down. This feature reveals a deeper message. Not all forces exist to transfer energy. Some exist to constrain motion. Magnetism belongs firmly in that category. It shapes paths rather than fuel levels. In doing so, it hints that interaction can guide behavior without paying an energy cost. That idea extends to large systems. In a motor, magnetic influence guides charges through coils producing rotation. Energy enters from an electric source, but magnetism itself acts as the organizer, steering motion into a useful form. Remove magnetism and the same energy produces nothing but heat. The presence of magnetic structure turns raw energy flow into coordinated motion. Coordination appears again in Earth's magnetic influence. Motion of conducting material deep inside the planet generates a magnetic region stretching far into space. That region guides charged particles arriving from the sun. Some particles spiral along magnetic directions and strike the atmosphere near the poles, producing auroras. Without magnetism, those particles would arrive differently, depositing energy in other ways. Magnetism shapes how energy reaches the planet without creating that energy itself. This shaping role invites a broader interpretation. Magnetism does not act as a source. It acts as a rule set that channels motion. Space near moving charge carries instructions rather than force in the usual sense. Those instructions tell charges how to move given their own motion and charge. That viewpoint alters how interaction feels. Instead of objects reaching outward to pull or push, interaction emerges from local response. A charge reacts to conditions at its own location. Those conditions arise from motion elsewhere, but the response remains local. Nothing leaps across distance. Each point in space supplies guidance, and charges follow that guidance as they move. This local response framework resolves a long-standing puzzle about interaction at a distance. Magnetism never requires instant communication. Changes propagate through space at a finite speed. Magnetic influence spreads as changes in space itself rather than as signals sent directly between objects. Light offers the clearest example. Accelerating charge produces changing electric and magnetic influences that travel together through space. These changes reinforce one another and move outward as waves. Nothing material carries them. Space itself supports their travel. Magnetism participates fully in this process, paired inseparably with electric influence. That pairing suggests something profound. Electric and magnetic influences do not exist independently. They form two aspects of one structure. Change one and the other follows. Remove either and the structure collapses. This structure reshapes how physics views space. Space does not merely separate objects. It stores information about motion and charge. It carries direction, strength, and timing. Interaction unfolds through that stored information rather than through direct reach. Here lies one of the most surprising outcomes of magnetism. Space gains physical properties, not substance, not mass, but structure, direction and timing embedded throughout. Magnetism reveals that structure in a particularly direct way. This realization affects how laws of physics appear. Laws no longer feel like commands imposed on objects. They read more like rules describing how space and time respond to motion and charge. Objects follow those responses automatically. That framing helps explain why magnetism appears unavoidable. Given charge, motion, and space behaving consistently, magnetic influence follows without choice. No adjustment or tuning removes it. It arrives as a consequence rather than an addition. A second consequence appears in how observers describe interaction. Electric and magnetic influences depend on relative motion. Two observers moving differently describe the same situation using different mixes of electric and magnetic influence. Both descriptions remain correct. Both predict the same measurable outcomes. This does not introduce ambiguity. It reveals flexibility built into description rather than into reality. The underlying structure remains the same. Motion determines which aspects stand out. That flexibility shows that magnetism and electricity are not separate pieces waiting to be combined. They are already unified. Description separates them for convenience. Nature does not. This unity leads directly to a striking limitation. Magnetic influence never appears without electric charge. No isolated magnetic charge has ever been found. Cutting magnets never produces a single pole. Each piece carries its own pair. Magnetic influence forms loops, never beginnings or endings. That loop structure reflects motion-based origin. Since magnetism arises from moving charge, and since charge itself supplies the source of electric influence, magnetic influence lacks independent sources. It circulates through space instead. This circulation explains why iron filings arrange themselves in looping shapes around magnets. The filings respond locally to direction embedded in space. They trace structure rather than creating it. Looping influence also explains stability in magnetic systems. Closed paths allow influence to persist without draining energy. Currents loop, magnetic influence loops. Systems hold their form through balance rather than constant supply. That balance plays a role in atomic structure as well. Magnetic interactions between electrons contribute to bonding, material properties, and chemical behavior. Atoms rely on magnetic rules as much as electric ones. Remove magnetism from atomic physics, and matter itself changes character. At larger scales, magnetism shapes stars and galaxies. Charged particles moving through cosmic space generate vast magnetic regions. Those regions guide plasma, shape stellar winds, and influence galaxy formation. Again, no new rules appear. The same principles scale upward. This consistency across size raises a deeper question. If magnetism arises automatically from motion of charge, and if motion depends on energy and space-time structure, then magnetism reflects how the universe encodes change itself. It sits at the intersection of motion, interaction, and geometry. That intersection carries meaning. Magnetism shows that interaction depends not only on what exists, but on how it moves. Identity alone does not determine behavior. Motion participates fully. This realization weakens the idea of objects as isolated entities. Objects carry charge, but interaction depends on motion through shared space. Relationship replaces isolation. Context replaces absolute behavior. That shift affects explanation itself. With this perspective, magnetism stops appearing as a topic confined to compasses and metals. It turns into a window onto how interaction works at every level. Motion shapes influence. Space encodes response. Energy flows through channels rather than through brute force. And from there, attention naturally turns to an even deeper layer where magnetism joins other interactions in revealing how constraints, symmetries, and limits organize physical law itself. That attention naturally turns to an even deeper layer where magnetism joins other interactions in revealing how physical law stays consistent across scale and circumstance. By this point, magnetism settles into a single unified picture. There is no need for extra ingredients, hidden mechanisms, or special exceptions. Electric charge exists. Charge can move. When it does, space and time respond in an organized, predictable way. That response shapes how charges affect one another. This framework is powerful because it does not change from situation to situation. The same underlying principles explain a vast range of phenomena that, on the surface, appear completely different. A compass needle rotating toward north, an electric motor spinning, a generator producing current, radio waves carrying signals across continents, light traveling through the vacuum of space, and charged particles bending inside laboratory detectors all arise from the same rules. What differs in each case is not the law of physics being used, but the arrangement of charges and the way they move. In every example, electric charge is present. In every example, motion plays a role. And in every example, space and time provide the structure that determines how that motion unfolds. Magnetism does not appear as an independent force layered on top of electricity. It is inseparable from it. Together, electric and magnetic effects form a single interaction described by one coherent theory. Physics has established several facts about magnetism with extremely high confidence. These are not philosophical ideas or speculative interpretations. They are conclusions drawn from measurement, experiment, and repeated verification across many scales of nature. First, magnetism always accompanies moving electric charge. Whenever charges move relative to an observer, magnetic effects arise. If there is no charge, there is no magnetism. If charges are present but completely stationary, magnetism disappears. This rule holds without exception. Second, magnetic influence always acts sideways to the motion of a charged particle. Unlike electric forces, which can pull or push along the direction between charges, magnetic effects deflect motion rather than speeding it up or slowing it down. A charged particle entering a magnetic region curves, spirals, or changes direction, but its speed remains unchanged if only magnetic forces are involved. That leads directly to the third point. Magnetic interactions do not change a particle's energy. Because the magnetic effect acts perpendicular to motion, it redirects movement without adding or removing energy. This is why magnetic fields are used to steer particles in accelerators and detectors without accelerating them. Energy remains constant while direction changes. Fourth, magnetic influence forms continuous closed patterns. Magnetic effects do not begin or end at isolated points. The structures associated with magnetism always loop back on themselves. This property distinguishes magnetism from electric charge, which can exist as isolated positive or negative sources. No experiment has ever observed a magnetic monopole, a single isolated north or south magnetic charge, despite decades of searching. Fifth, electric and magnetic effects are not separate phenomena. They are two expressions of a single underlying interaction. Which aspect appears depends on motion and perspective. A situation that looks purely electric from one frame of reference may appear as a mixture of electric and magnetic effects from another. This unification is not a matter of interpretation. It follows directly from experimental results in the structure of relativity. Sixth, changes in electric and magnetic conditions do not propagate instantaneously. They spread through space at a finite speed. That speed is the same for electromagnetic signals, radio waves, light, and all related effects. This limitation ensures that cause precedes effect and preserves the consistency of physical law across space and time. These principles have been tested in laboratories, confirmed in technological applications, and observed in nature. They apply at the scale of atoms, where electrons move within quantum structures. They hold in engineering systems like motors, transformers, and communication networks. They govern planetary magnetic fields, solar storms, and radiation traveling across interstellar space. The same equations describe all of it. Just as important as what physics knows is what magnetism does not do. Magnetism never appears on its own. It never exists without electric charge. It never supplies energy by itself. Any device claiming to produce unlimited energy through magnetism alone fails when tested. Magnetic effects cannot be separated from motion, and they cannot operate independently of the broader electromagnetic framework. Any explanation of magnetism that violates these constraints fails experimental scrutiny. Proposals that treat magnetism as a standalone substance, a hidden fluid, or an independent force break down when measurements are made. Physics advances not by inventing mechanisms that sound intuitive, but by rejecting ideas that conflict with data. At the same time, it is important to recognize where understanding remains incomplete. Physics does not yet possess a fully unified description that seamlessly combines electromagnetism with gravity at the deepest level. While both are extraordinarily well tested in their own domains, their integration under extreme conditions, such as those near black holes or during the earliest moments of the universe, remains an open challenge. There are also practical limits. The detailed magnetic behavior of complex materials can be difficult to calculate from first principles. Strongly interacting systems, exotic quantum materials, and turbulent plasmas under intense magnetic conditions continue to push the limits of current theory and computation. In astrophysical environments and fusion research, magnetic dynamics often reveal unexpected behavior that requires new techniques to understand. These gaps do not signal contradictions. They reflect complexity. The core framework linking magnetism to electric charge, motion, and space-time structure remains solid.